Have you ever wondered how stiff a guitar string really is? In this video, we'll uncover one of its fundamental material properties, Young's modulus, using a clever physics experiment. Instead of stretching the string by large amounts, we'll measure incredibly tiny changes in its length using mirrors, light, and a telescope. Let's see how physics allows us to measure something almost invisible. We will indirectly measure the Young's modulus of an acoustic guitar string. This string is made mainly of steel. Similar to the previous video titled Measure Shear Modulus of a Brass Rod, Practical Torsion Physics Experiment Explained, we will use the defining relation for Young's modulus, E, where sigma is the normal tensile stress and epsilon is the relative elongation of the string. The normal stress is the ratio of the force stretching the wire along the length of the string to the cross-sectional area S of the wire. The relative elongation of the string, epsilon, is the change in its length divided by its original length, L0. The normal stress can be easily produced by hanging weights with mass m and calculated as the ratio of the effective gravitational force of the hanging weight to the cross-sectional area of the string with a diameter d. The value of the effective gravitational acceleration depends on the location of the experiment on the Earth's surface. For the location where the experiment is performed, the value of the effective gravitational acceleration can be easily found on the Internet. The diameter of the string d can be measured, for example, using a micrometer with an accuracy of 1/100th of a millimeter. If you don't know how to use a micrometer, watch my video titled How to Read a Micrometer, 0.01 millimeters precision, explained in 58 seconds. If we measure the dependence of the normal stress, sigma, on the relative elongation of the string, epsilon, and fit the measured point in the graph with a straight line, the slope of this line will be our estimate of the Young's modulus, E, of the string. To obtain Young's modulus in units of pascals, we will also plot the normal stress in pascals, since the relative elongation is dimensionless. However, to calculate the relative elongation, epsilon, of the string, we need to measure the change, L minus L0, in the length of the string. And this change of the string is very small and difficult to measure directly. Therefore, we will measure it indirectly by observing the change in the tilt of a small mirror. The elongation of the string caused by the tension slightly tilts the mirror, which results in a change in the scale division observed in the mirror's reflection. The reflected scale is observed through this small telescope. When the mirror's surface angle changes slightly, the light beam travels a long distance from the scale to the mirror and back into the telescope. The objective lens of the telescope is close to the scale. Therefore, a small change in the mirror's tilt angle caused by a small relative elongation of the string produces a larger change in the scale division observed in the telescope. Instead of measuring the change in the string length, L minus L0, we will therefore measure the corresponding change in the observed scale division, S minus S0. This change in the observed division S minus S0 is directly proportional to the change in the string length, L minus L0. Let us denote the proportionality constant by K. This follows from the geometry of the experimental setup. Twice r is the width of the mirror. The mirror rotates about its center. The displacement of the edge of the mirror, alpha times 1/2 of r, is approximately equal to the elongation of the string, delta L. The constant, K, can be determined, for example, by a calibration measurement, in which the stretching of the string caused by hanging weights is replaced by a precisely defined elongation, 1/2 of delta H, produced by turning a micrometer screw. By turning the micrometer screw by delta H, we can directly measure the elongation of the string delta L, which is equal to 1/2 of delta H. We can therefore measure the absolute elongation of the string with an accuracy of 1/100ths of a millimeter, while simultaneously measuring the corresponding change in the observed scale division, delta S, in the telescope. From the geometry of the experimental setup, it follows that the ratio of delta H to delta S is twice our proportionality constant, K. Therefore, before measuring the actual dependence of the normal stress caused by the weights on the elongation of the string, we first create a calibration graph showing the dependence of delta H on the change in the observed scale division, delta S, in the telescope. The slope of the straight line obtained by fitting this calibration graph will be twice the proportionality constant K, as we saw in the previous slide. We will then use this constant to convert the change in the observed scale division, delta S, into the relative elongation, epsilon, of the string caused by the normal stress produced by the hanging weights. In summary, first we create the calibration graph, and only then do we create the graph of the normal stress, sigma, on the relative elongation of the string, epsilon, which was shown here before as the first one. By combining careful measurements, a simple calibration, and a bit of geometry, we were able to estimate the Young's modulus of a steel guitar string. Experiments like this show how powerful indirect measurement can be. Even the smallest changes can reveal important properties of materials. Thanks for watching, and if you enjoy experiments like this, don't forget to subscribe for more physics demonstrations.